Hello everyone. Today I would be presenting a work on image restoration titled SFCola-Net Spatial Frequency Collaborative Attention Network for Image Restoration. I will start off with brief introduction about the need of image restoration and limitation of current methods. Then I will show a brief frequency domain analysis of these degraded images, and based on these analysis I will explain the spatial frequency non-local patch-based attention module, which would be a feature extractor in our whole architecture, and move to explain the entire architectural details. Finally, I will conclude with some results and outcomes. Image restoration plays a fundamental role in improving the quality of images that have been degraded due to environmental factors such as haze, rain, or poor illumination. These degradations significantly affect the performance of high-level computer vision tasks like object detection tracking. Therefore, it is crucial pre-processing step. Traditional models or traditional methods relied on physical models or handcrafted trials to address these problems, but they often failed under complex non-homogeneous degradation. Deep learning models, on the other hand, learn directly from the data, allowing them to adapt to diverse degradations. However, conventional CNN architectures based on encoder-decoder structure suffer from limited receptive fields, making them ineffective in capturing long-range dependencies. To overcome these, self-attention and transformer-based architectures have been explored, but they come at high computational complexity and often overlook physical characteristics of degradation, leading to overfitting or poor generalizability. We performed an analysis in Fourier domain to understand how these degradation manifest in spatial and frequency components. Here, by interchanging the amplitude and the phase components between the degraded and clean images, we observe first, the degradation primarily affect the amplitude spectrum, and second, phase retains the structural details of clean images. These observations motivated us to build a model that can jointly leverage spatial and frequency domain features for effective restoration. Based on these intuition, we designed spatial frequency non-local patch-based attention module. We take three branches Q, K, V and extract the spatial and frequency domain features from the branch Q and K. The spatial domain extractor focuses on pixel level relationships to model local and contextual dependencies, while frequency domain extractor leverage frequency spectrum to identify global patterns and structures. We find cross attention between these feature maps. Instead of directly reshaping QKV for pixel level relationships computations, our method extracts non-local patches between these feature maps and calculate the relationships for the attention between these patches. And finally, all these patches are folded back together to give enhanced feature map. Building on this, we propose the entire SFCola-Net architecture, a multi-scale architecture that combines local and global features. This architecture takes the inputs in three scales and generate the corresponding outputs for each scale. As feature extractor, we combine the non-local patch-based attention and local feature extraction module and use it in the encoder-decoder structure. After each feature extractor in the encoder part, we downscale the feature map and concatenate the features from the corresponding scale before giving it to the another feature extractor. Similarly, we design the decoder part. In encoder and decoder, we tested out two different approaches, skip connection and multi-scale fusion module. We found that adding a multi-scale fusion module, which itself is a patch-based self-attention architecture, gives improvement in overall performance with negligible overhead in terms of computational complexity. The entire architecture is trained in a supervised manner by combining spatial, frequency, and edge level losses. A contribution of each loss is given in this table. Finally, the weighted average between a multi-scale combination of spatial, frequency, and edge level losses gives us the best performance. Moving to the results, this slide shows the de-hazing performance on HSTS datasets. As we can see from the visual comparisons, our model uh, effectively removes the haze and recovers the natural contrast and the colors. Quantitatively as well, SFCola-Net outperforms several state-of-the-art methods. Similarly, for deraining tasks we evaluated on IRS dataset, our method produces much cleaner images with minimal residual range tricks. Both qualitatively and quantitatively metrics confirms the robustness of SFCola-Net across multiple weather conditions. Further, we also applied the same network for low light enhancement on LOL dataset. The results show that our network enhances the illumination without oversaturation or loss of details. Additionally, we have evaluated our model for generalizability across multiple datasets for dehazing and deraining. Across all these datasets, we have got improvement in PSNR and SSIM values while maintaining a modest computational complexity. These are the references used for the comparative used for comparisons. Thank you.